Hello, everyone. Walton, as Olivia said, Flamur, I work for AWS. I'm a compute specialist, which means a lot of things. But among my day-to-day job, I am also part of the technical oversight committee at FINOS, which means we're the body that governs how we accept projects, how projects evolve, what the life cycle is for the whole of FINOS as a foundation. It's comprised mostly of volunteers like myself, so we don't work for FINOS, we just volunteer part of our day-to-day jobs. Before AWS, before FINOS, I worked for JP Morgan. I was the cloud architect for a platform called Athena, which is the biggest risk and trade management platform in the world. So I do have quite a lot of financial services background as well. But on top of that, that also comes with the HPC aspects, because one of the things that all of these banks, investment banks do in capital markets, actually they have a lot of risk calculation that happens at the end of the day. All of that stuff tends to run on something called an HTC-Grid. So why did this start? We have a lot of customers that we work with across the whole of industry, and they all have the same problems that they try to solve. There is a lot of increase in market volatility with all of the latest financial services, or the stuff that happened in 2018, 2008, the last few years after COVID. So this actually requires them to run a lot of risk calculations with new scenarios, with all the stuff that happens. We saw that all of these banks, in addition to actually requiring more compute, they needed to look at other ways to get that compute. On-prem was just not scalable enough at the time. So everybody started looking at the cloud. So we're talking about 2015. And when looking at the cloud, there were like a couple of options. Either you would have to bring what you already have from on-prem, or you would actually have to redesign for cloud. So some of these customers took the aspect of actually we're going to re-architect in a cloud native way. And everybody kind of went through that design phase of what would an HPC system in a cloud native world look like? And I did the same when I was at JP. So we built a platform from the ground up for cloud and went through a whiteboarding exercise as what would this look like. So getting all of those learnings from the different customers that we had, we came up with what we call a blueprint, which was a solution that we wanted to give the industry to actually be able to say, okay, I have already something to start from, and I'm going to adjust this for my platform or for my environment rather than actually have to go through that whiteboarding exercise every time. So HTC-Grid was built as a blueprint to help financial services customers build HPC platforms in a cloud native way. And we actually started this at AWS at about 15, 16, and then donated it to FINOS about almost 2 years ago. So now it's a FINOS project, and we are hoping to increase the reach as well as the usability of this across multiple customers. It's already in use in multiple financial services banks. I can't say who, but it's already in production in multiple places. So how many of you are financial services folks? How many of you know what this is? But if not, I'll just do a quick run through. So ultimately, as I said, there is this thing called a risk that is run at end of day, throughout the day, on demand by traders that trade on a trading desk. And they are actually trying to calculate whether they can make a certain trade and how does that affect their risk profile as a business as well as a desk. So in order to do that, they go through this kind of pipeline that does some of the scenario generation. That just means like I'm actually going to look at all of the different scenarios that I'm calculating risk for. I'm going to get all of my market data, trade data, which actually affects how this works, prepare that data in a certain way. And then the majority of the time is spent in this calculation bit. That's where a process called Monte Carlo simulation happens that runs in a very parallelized compute. So there is a lot of horizontal scale compute that this runs on, and it's basically the same kind of simulation or the same kind of calculation with different inputs. So that actually just a lot of churning basically. And then once that's done, you'll have some post-processing of that data. and then you'll store that for P&L reports, for upstream, downstream systems, and so on. So this is the whole flow, but ultimately we're going to concentrate on this HPC compute grid portion. So that works because we have these two components here. We have the risk engine and the QR library. So those are the things that actually have that logic. That's the secret sauce that those companies have around calculating that risk or being able to ascertain whether something is a good trade or not. So considering that, as I said, you have certain types of risk, but end of day tends to be the most compute intensive, because that is start something at the close of the day. So when the London Stock Exchange closes and NYSE closes, whatever, then from there onwards for about 8 hours until the next day, they do a lot of calculations. So as you can see here, say it starts around 4 or 5, and then until the next morning, you have a lot of it. And then during the day, you have some, which is this on-demand risk or live risk that they do for parts of the business, but the majority of the stuff is spent on this end of day batch. So banks, again, due to market volatility, all of the different factors, but also actually just being able to do this faster, better, so that they can get those insights faster and act on them, maybe during the night or a different business and so on, or a different exchange altogether. They want to shorten this time. However, in order to actually be able to do that, as I said, because this is a horizontally scalable workload, technically you can just increase the compute and then you can do that faster, right? But again, on-prem, that was not a thing. So the ability to run on the cloud makes it possible, because then we can scale horizontally even further. That being said, there's another aspect of this, which is actually very important, and that is the nature of those tasks. So HPC as an umbrella is a term that you can use across multiple industries. Fluid dynamics has HPC, genomics has HPC. There are a lot of industries use a lot of compute to calculate stuff. It does have a very different task profile though. That usually comes from how the calculations are done, but also how the actual scheduling is done. So in, say, again, fluid dynamics or genomics, they are what we call tightly coupled HPC workloads, because they all have to run at the same time and finish at the same time. If one of them breaks, that's it, done. Versus in HPC, it's for financial services, it's a lot more horizontally scaled, but they're loosely coupled. So they can do their own calculations without actually depending on each other. But the task duration is also a very important thing, because there is a certain cost to scheduling something to run. There is a whole thing that has to happen through the HPC system for a task to finish. So this is actually real data from a customer, and they calculate about 270 million tasks per day on a end-to-day run. And of those, about 40% are less than a couple of seconds. So the task actually would finish in less than a second. So if you're actually spending about 2 seconds to schedule it, you're already wasting time, right? So the nature of the workload, the way that the task duration happens, actually affects the end-to-end performance of such a system. That's why we say that for financial services, you need a high throughput compute. You will actually have what we call an HTC system rather than HPC. It's not just high performance compute, you also have to have the high throughput. So that brings us to HTC-Grid. Again, it's a cloud native blueprint that we started at AWS, and it is a high throughput system. It's actually able to scale and handle all of these short running tasks, and it actually uses cloud native services from the get-go. That's the project URL. I'll show you more in the end as well. So when we did design HTC, we actually had some tenets in mind around how would such a system look like. So obviously it had to be cloud native. That's kind of the whole point, so that you don't depend on any services. But as I said, the scale, the throughput, and the latency were deciding factors. And this came because the nature of the workload is such that we need to be able to handle that, but also because of that example that I showed you of 270 million tasks, that means a lot of compute, right? So usually these platforms tend to run in tens, hundreds of thousands of vCPUs. So that is a lot of compute. I have customers that go beyond the hundreds of thousands for a platform. So that means you're actually able to scale very much, but also very fast. We have tested HTC-Grid to up to 80,000 vCPUs in one single installation, and it can go further. We have not pushed the boundaries in our tests. Of course, as I said, in production, customers run it in larger scale. We have tested it up to 30,000 tasks per second. So if you had 30,000 tasks and you schedule through HTC, so I say zero-sum task, which means I'm doing exit zero. Like the task itself is not doing calculation because obviously that depends on how long the calculation would take. But if I have exit zero as my task, I can push 30,000 tasks and they will all finish in 1 second. So the end-to-end schedule and round trip time for HTC about 0.3 seconds. So from when you schedule it until it makes it to the other end is 0.3 seconds, which is crazy numbers, right? Modular is something that we have taken very into heart, and you'll see the way it actually works, but everything is composable. So we're able to click and swap different components for a different flavor of it, which is also part of why this is important for FINOS. I'll dive deeper onto this bit later about why all compute is Lambda. And of course, because such platforms run at scale, they also need to support a diverse list of purchasing options when it comes to cloud, because you have to be able to run this economically, otherwise it doesn't make sense. So running on demand and spot compute, as we have it on AWS or other cloud providers have a similar concept, is actually very important because you're able to welcome, no problem. Okay, so I'll restart. Okay. So we will talk about things that will make it still clear to you guys. So hopefully you're not too lost, but feel free to ask questions. Again, on-demand spot, all of the different purchasing options, and then replatforming. Come on, one more. That is the ability to use all of the latest and greatest that the world has to offer in regards to software as well. So both from being able to use the latest operating systems, to being able to use the latest architectures, to kernel options, to processes, this actually makes it very easy to swap to whatever other system that you would like to incorporate in your platform. So we took all of these to heart when designing HTC. Everybody loves an architecture diagram, so here it is, and then I'll walk you through what all of the different components are. So again, such systems tend to be fairly similar in nature. I say this with tongue in cheek, but in 2025, nobody should be designing a scheduler anymore because this has been done a quadrillion times. There's so many versions out there. Nobody else should build one other than me. Don't do it. There is the client side, which knows how to speak to the system. Of course, there's a configuration file, etc. But ultimately, you have your connector library that knows how to connect to HTC, and then it will talk to the different components here. So when you schedule a job, which is comprised of, say, multiple tasks, you'll have what's called a task definition and a task payload. And the reason we split this has to do with partly some limits on, say, how big an HTTP request can be, but also you don't necessarily want to ship all of your data together with your tasks. So if you remember in that risk pipeline that I showed you earlier, just for the benefit of the other guys. So if you see here, there's a lot of data fetching and preparing that happens beforehand. And that is combining all of the data that's actually important to run a certain task. So if you actually bring all that data together, you can actually then save that task payload in what we call the data plane. And again, that modular nature is apparent here as well. So we have different flavors that you can pick and choose which one you want. So it could be something in like an S3 bucket, or it could be Redis if it's faster, or FSX and so on. So those are all different services that allow you to store that data, the task payload, that is then going to be accessed. And then you have the task definition, which the connector library sends through to the control plane. So think about the task definition as something like just metadata that allows you to connect all of the different parts about what are you running, like what libraries are going to use, what version, and so on. And then that goes to the control plane. We will look at the deeper architecture diagram here for the control plane, but ultimately, for all of the things, again, cloud native being a keyword, we wanted to use serverless services. What that means is when this platform is not doing anything, the control plane is basically a zero cost because there's nothing that is always on. You only pay for what you use when you use it. But also, this is what allows it that massive parallelized scale, because when you're using serverless services, say every single task that gets submitted is another whole parallel run of stuff. So you can just continuously submit more and more, and they will all just parallel scale. The control plane is using Lambda, is using DynamoDB, is using API Gateway and SQS, which, while this was, again, built at AWS, this can and will work in every other cloud provider in the same way, even potentially on-prem. So all of these services have a equivalent that runs basically everywhere. Lambda, again, AWS invented it, but every other cloud provider has a service that is similar. Dynamo is just a KV store. SQS is just a queue. API Gateway is just an API Gateway. So technically, this can run anywhere. And then the actual compute plane is where the actual work happens. That's where the calculation happens. So while the control plane is just basically taking the task, storing it, putting it on a queue, we use what we call a pull-based system. So ultimately, the compute looks at that queue and then brings up nodes that will pull tasks from that queue to run calculations on. Once they're done, they store the results, and then they go and pull on more tasks as well. As I said, I'll do a zoom in, similar architecture, but you can now see the actual building blocks. So again, the task definition goes through the connector library, makes a call, it's basically just REST, makes a REST call to API Gateway, which then triggers a Lambda. Again, it's a serverless service. And then it says, okay, I'm triggering the submit Lambda because I'm submitting the task. And the Lambda takes that task, stores that metadata in Dynamo, puts the task in the SQS queue, and then the compute plane here. So in this example, we're looking at the EKS version, which is basically managed Kubernetes. If you are familiar with Kubernetes, it's a container-based system, and it actually looks at that queue and uses the queue depth, which means how many items are in the queue, as a means of actually triggering the scale up and scale down of the platform. So by doing that, then it actually says, okay, I have 1,000 items in the queue. Of course, you can configure it to say every worker can handle 10 tasks at a time or something like that. So then it says, okay, if I have 1,000 and I have 10 tasks, so I'm going to bring up 100 pods. A pod is one or more containers. So a pod becomes a node, and as far as like HTC is concerned. And one such node comes up and then goes and picks up tasks from the queue, says, give me 10, go and calculate, give me another 10, and so on. So this actually drives the automatic scaling. This is very important. The reason I'm saying this is because we're not actually building anything ourselves here. There is no secret or custom sauce. This is all just cloud native services doing what they do best naturally for the scale of the system. So again, the serverless services are driving that automatic scaling. They're allowing us to be able to scale up faster and higher. And then the compute is actually just using horizontal pod autoscaler with something called CADA, looking at the queue and actually scaling up compute. So again, everybody's doing the best thing that they can do, so that single responsibility principle is very much at use here. And then when we store, we save stuff in, like, as I said, S3 or Redis or FSX, which again, those are all storage services that allow for scale and speed and storing the results. And they're pulled back from the on-prem as well. Now, if you remember, I said this thing called all compute is Lambda. That is a very interesting and important kind of idea on how HTC works. So if you just zoom in here, as you can see, a HTC node is comprised of, as I said, within a pod of two containers. One container is the agent container, and the other container is the Lambda container. The agent container is basically responsible to go and look at the queue, get items from the queue, and then say, okay, I'm going to work on them, and then submit them to the Lambda container for the actual calculation. The reason this is important is because, say, in a financial services company, they will have, as I said, this thing called a quantitative analytics library that is used for the actual calculation. But since we're at API days, everybody who builds any type of software is going to have a different API. And there is no consistency whatsoever. Even within the bank, there will be multiple analytics libraries, and they will all work differently, and different versions and so on. So the ability to say, okay, I'm going to build a system that works with all of them becomes impossible, because how would such a scheduling system know how to submit to the other library that speaks a different language? So as I said, AWS built AWS Lambda as a service, but on top of that, we have also open sourced the Lambda API. And that is actually a very cool thing, because as far as this kind of workload goes, it's pretty much the same problem. The Lambda API says, I need to know what function am I going to run, what input am I getting, and here's your result. That's all it cares about. There's nothing else in the API. It's just function name, input, output. That's it. So in that way, we say, I'm going to bring you, as the person who's using the blueprint, you bring your own quantitative analytics library, and then you integrate it here within the Lambda function. So that Lambda is basically told, in order to actually start this version of the quantitative analytics library, you need to call this API, and you need to pass in the inputs in this way. But as far as the rest of the system is concerned, I'm only speaking Lambda API, period. So ultimately, that's our entry point to the function, and then the integration happens here. That's also why we call this a blueprint and not a product, because there has to be some integration done to actually plug your stuff in, which is understandable for any software project, but that's where that integration works. Yes?
Every bank is on one.
Not just. Every single asset class tend to have one, which is actually insane, and different versions. Yeah. So the integration just would become impossible, basically. So again, this was made for the whole industry, so then anybody can plug in what they want. But that allows us to achieve that. Okay, I'm gonna pause because I'm out of breath, but also any questions up to here? Yes.
Question about
Yeah, go on.
Lambda cold starts. Does it not pose any issue?
So again, I am every time I give this talk, every time somebody asks a similar question, then I have to go and try and explain again. This is just using the Lambda API. It is not the AWS Lambda service. So it is running inside a container. It is as far as this goes, right? In here, that is purely just the API, because the API is open source. We are not using the AWS Lambda service. Here, yes, but the Lambda cold start is a issue for things like Java, where you have to actually start the JVM and load stuff into memory. For this, we use Python, which is super, super fast. So yeah, cold start, not an issue. Any other questions?
The first slides, you control the density of how easy. I heard that there are some trying power.
Mhm.
Is it
So I think, again, this is, say, 9 to 5 is the traditional trading day. When a exchange closes, the banks have to report a stance of risk as far as the business goes to the regulator. That is, based on all of the trading we did today, what does our risk profile look like? That tends to be, I'm going to calculate every single thing on every single desk across all of the trades, because it could be that you have trades that are still open from 20 years ago. So that is a lot of recalculation being done. But that is just from a regulator perspective. Now, even if, like, say, an exchange made trading 24 hours, you will still continue to run this part, which is intraday. I'm always, before I make any trade, after I make any trade, I actually look at what my risk profile looks like. And also, say, certain desks or certain businesses tend to do what we call on-demand risk, which is actually, I don't know, it's 2 p.m., but I still want to know how am I looking. So they will trigger parts of the business, but being able to calculate everything is actually a interesting problem, because again, it's a numerical calculation. Now, among all of the different regulations that have come out in banking, there is this thing called FRTB. And for the FRTB regulatory reporting, we expected that there would be a much higher increase of compute usage from the banks, because that requires more reporting, more calculations, different scenarios. Did not necessarily just happen, although, like, it's not in production. It's not enforced until 27, I think. But ultimately, banks are still, like, thinking about doing that. Some banks and some businesses out there have taken a more analytics approach to this. So they have looked at, can we use, like, data analytics rather than recalculation, stitching data across to actually get those numbers. That could be an approach. So I think there are potential, like, I don't know, things like quantum or things like Gen AI, ML for actually at least doing part of those things. We can't use it necessarily for reporting, but get an idea. So there are ways that actually firms are looking at this, but there's no solution. There's no problem yet. It would be actually hard. But again, if that happens, then further horizontal scaling, that could also be the solution. Right? Instead of using, I don't know, 100,000 cores, use 5 million. Let me finish fast. Okay, so if no more questions on the architecture diagram, I'll give you a brief demo. So let's see if this works. Can you see it? Oh, not yet. No. Does it display correctly? So I'll tell you what I have here. So in these two bottom boxes, I have the logs from the agent container and the Lambda container in the pods. Now, as I said, if you remember, this is the Lambda container output, basically. And again, because you're actually just implementing the API is very standard, it just says, I got this call for this request ID, I succeeded, I had a duration of this long, and I used this much memory, and I billed this much time. Again, this is not necessarily relevant for the agent container here, because, for the Lambda container, sorry, because we're not charging per second. It's an always-on service, but that's just the API, right? But the duration, for example, is an important part. And here we're just actually logging all of the bring me tasks, bring me results, and I'll show you what I did. So here, I'm going to start a run. So what's actually happening is I created an instance of that client, and I said, okay, I'm going to submit some tasks to you. We are actually using something called QuantLib. if anyone is familiar with it, is an open source quantitative analytics library that exists out there. No bank really uses this in production in real life because they all have their secret sauce. But this is a full representation of what such a QR library would look like. And we have that plugged in into this deployment of HTC-Grid. So ultimately, I am sending, I think I configured it for 10,000 pricing of options. So we're doing some USD and Euro options for like the swaps desk and in rates. And we say, okay, I have those 10,000 different trades and I want you to price them. And at this, like, as you see them, they're sent to the system and it says, okay, I was running one single pod. I just had one pod sitting there and waiting, but I have seen that I need to do some more work. So I am scheduling more pods to start. And as you can see here, that one pod that was running is already like creating results. So you'll see it's 30, 31. So it's going through those pricing options because it's doing work. But then the system recognizes that I needed more to be able to do the compute. And as I said, it's a fully auto-scaled system. So when it's not doing anything, there's nothing like running. And when it actually starts doing stuff, looks at the queue and automatically scales. So we were at 1, 4, 16. Now, you have to be mindful that starting a computer takes about 2 minutes, generally speaking. It's somewhat similar in the cloud. So it takes anywhere between, say, 30 seconds and, I don't know, it can go up to 10 minutes depending on what you're doing to start an instance. But once those instances have started, so as you can see here, we were at like 3, went to 4, and then suddenly we will actually increase much more. But the 10,000 things that I scheduled already finished. Like I can see here, like you have the portfolio value of X. So the actual stuff already computed, even with the 1, 4, 10 pod. And even if you send 1 million tasks, this is still gonna continue or work in the same way. Let me show you what the scaling dashboard looks like. So this is the last 30 minutes of how that system was working. It basically had nothing. It says, okay, I actually got 100 things to do. This 100 things was, as I said, price 10,000 of those things, but actually do them 100 at a time because there's no point in you trying to do every single one individually. So they grouped them and said, okay, I have 100 things to work on, did the automatic scaling. As you can see, then the task completion goes up and down because it depends on like what time I'm spending working versus finishing the task. And then like the agent count goes back down again. So again, the system started with 0, scaled up, did all of the work, scaled down again. And now that I have more, like I have 49 pods already running, say if I ran that same test again and I said, okay, do this again. Now I don't have just one, I have kind of pre-scaled the system because it warmed up for something else. You can see that actually the calculation finishes much faster than it did before because there's a lot more workers that can actually pick up tasks from the queue. And now it will finish in like a split second, right? So this is kind of part of that importance of such a system as well, that also in addition to how fast it scales, it tends to be dynamic because different asset classes, different parts of the business are going to schedule things differently at the same time, different times. So ultimately, such a system that would be shared among them, if that was the case, would actually be able to cater to all of their requirements. So the split logic and being able to handle horizontally parallelizable tasks is actually very important for both speed and scale. So with that, I will leave you with a couple more things. That's some of the resources on this. There is the repo project, and we have some blog posts on all of the testing, on all of the scaling that we've done. There is a workshop that exists, which allows you to run this whole thing yourself. If you have an AWS account somewhere, you'll be able to deploy this and actually be able to run the same test I did and do, custom stuff on top as well, blogs, white papers, and so on. It would not be an open source conference without saying this. We are looking for contributors. So if you are a AI developer, if you are a UI developer, if you want to do something on the back end, whatever it is you do, we would love to have you. Come find me, ask any questions if you would be interested. Again, as far as the stack goes, it's a lot of cloud native services, Python, the backend stuff, the agent container, Lambda container stuff is in multiple languages because our customers tend to use multiple languages. So we have a Java, Python, a .NET, C version, because it depends on what the integration points are. So any of those would be useful. Thank you very much for listening. Feel free to ask any questions.